So what I'm going to do now is, so first of all, let's list the corollary. Corollary of what we did is that every root system has a fundamental system. S. Now, if we have a fundamental system, then we can write down the matrix of all Cartan integers. Those are the integers n, alpha, beta. So definition, the matrix consisting of n alpha beta with alpha and beta elements of simple roots. So this is a square matrix. Its size is the dimension of E, and it's a square matrix of integers. This is an element of called the dimension E by dimension E matrices with integral entries. And this matrix is called the Cartan matrix. Associated with S. Now, of course, the matrix is not complete. It's not unique because, first of all, no ordering of S is specified. So up to ordering of S, it's unique. Now, one could also observe, well, the root system may have different fundamental systems. Indeed, this is true. There is a one-to-one correspondence between fundamental systems and positive systems, or Wine chambers. But now there is a result which says that the Wine group actually acts simply transitively on the fundamental systems. And that means that basically the Cartan matrix doesn't depend on the choice of fundamental system, because, I mean, if you just map bijectively by the Wine group element to another fundamental system, the resulting Cartan integers will be the same, but their index set will be different. That means that the matrix will be the same. I'm not going to discuss this in any detail now, but this Cartan matrix is really something that is associated to the root system. And our statement, and this is a statement that I want to prove, is that the root system is completely determined by this Cartan matrix. So from the Cartan matrix, so theorem equal to R is completely determined by Cartan matrix. Well, really, I don't even have to specify the index set. And so maybe it's, now, of course, we can list basically all Cartan matrices. Let's order the of rank, say, rank 2. So maybe we should first do that. Find out the Cartan matrices. So assume that the dimension of E is 2. Now that means that we have two simple roots. Now think of the table that I started with at the beginning of this lecture. We know that simple roots are usually obtuse, meaning that their inner product is at most 0. Now, 0. Now, if you order the roots according to their root length, then then the n alpha beta are completely, all possibilities are completely known. And this results in the following possible matrices. The matrix 2, 2. It's always 2 on the diagonal, because on the diagonal it will be 2 alpha alpha over alpha alpha, which is 2. And then the first one is this one. And then the second one is this one. So let alpha be the shorter root than, well, the second one here, so it's this one. The third one is this one. And the fourth one is this one. These are all possibilities because of the table that we specified at the beginning, and because of our knowledge that the inner products of alpha and beta are non-positive. And my claim is that if such a matrix is given, then so this is the column, say, corresponding to alpha, this is beta, beta. If such a matrix is given, then the root system is completely determined. And we know that there are no more possibilities in these matrices, and what we will show is that actually each matrix corresponds to a matrix. By the way, I also gave the definition of Dynkin diagram. A Dynkin diagram is a graph, the box of the graph, with some additional information. How do we get the graph? The graph is obtained by taking as vertices the simple roots. So we have 2 vertices. Now, we are going to connect vertices according to the product of the Cartan numbers, which is 0 here, no connection here, which is 1 here, 1 edge here, which is 2 here, 2 edges there, which is 3 here, 3 edges here. And in case of multiple edges, there is a ratio of the length of the roots, which is square root of 2 here, square root of 3 there. And this graph is made into a Dynkin diagram by adding an arrow pointing in the direction of the shorter root. So it's this is alpha, this is beta, and it's this in that case. All the information on these matrices is completely encoded in these Dynkin diagrams. So clearly, if you have a bigger Dynkin diagram, then you have the same kind of encoding of 2 by 2 submatrices. If 2 vertices are not connected, you will have this corresponding matrix, which may be a particular, for 2 particular columns of the corresponding particular rows, corresponding to those single rows, etc. Now, I'm going to prove the theory, and the crucial step is the following. That's formulated as a lemma. So for every root which is not simple, for every positive root which is not simple, beta can be expressed as the sum of positive and simple root. So there exists a, we can write it as follows. There exists a simple root alpha such that beta minus alpha is a positive root. So another way of saying this is that beta belongs to those roots that can be written as a sum of a simple root and a positive root. Now, what's the interest of this lemma? It means that every positive root can be reached from 0 by a number of steps. In each step, we are adding a simple root to the previous root. This may be done in a haphazard way. But the statement is we can do it in such a way that every root on the way, every sum on the way is a root. So we need not leave the positive roots, and then by adding one simple root at a time, we get all positive roots starting with 0. So clearly this is an important mechanism to decide what are our roots. Right? We start with the simple roots, and then we have to consider all possible. So now we can try to work with levels. We start with the simple roots, then we try to generate the roots that can be written as a sum of 2 simple roots, then we can try to generate the roots that can be written as a sum of 3 simple roots, etc. And at some point this process will stop, and then we have all our positive roots. That's the end. So, but first let's prove this lemma. So, suppose that so let alpha beta be a positive root, but not simple. Now assume that for all simple roots, assume that this is not true. And then I will arrive at a contradiction. Assume that for all alpha in S, beta minus alpha is not a positive root. Now, since alpha is simple, alpha minus beta is not a positive root, it's automatic. Because if alpha minus beta were a positive root, then alpha could be written as the sum of beta and the positive root, which means that alpha could be simple. Now, if both of these statements are true, then it means that beta minus alpha is not a root. But we've seen that this is only possible if the angle between beta and alpha is not strictly positive. So that means that these inner products are close to 0. Now we know that beta is a positive root, therefore it can be written as a sum of simple roots. So that means that beta can be written as a sum of the 1 up to alpha sum n, all simple roots. Multiplicities are allowed here. It's a sum of simple roots. And now we know that the inner product of beta with each of these simple roots is at most 0. So that means that beta inner product with itself by linearity of the inner product in the second slot, we can decompose this inner product as a sum of inner products with the alpha j's. Those inner products are all at most 0, so this inner product is at most 0. We also know that the inner product is positive definite, and therefore this implies that beta is 0, which contradicts the description. Therefore, we must be able to find a simple root, such that beta minus alpha is still a positive root. Okay. Now the idea is, an understanding that we know that if beta is a positive root, so now we get to the proof of the theorem. If beta is a positive root, it means that beta is expressible as a sum of nu alpha times alpha simple roots. And nu alpha are natural numbers and they are unique. And so we can define the height of beta. The height of beta is going to be defined as the sum over the coefficients mu alpha. Of course, the height of beta has also another interpretation. From the string of additions of simple roots through the positive roots until you reach beta, then the height is basically the length of that string. Okay, and now define P sub k to be those positive roots that have height k. So we know what P1 is. P1 is S. These are the simple roots. We also know that if we take the sums of positive roots of height k, and we add simple roots, so we consider all possible additions, then if we take the intersection with the roots, then we get the roots of height k plus 1. This is because of the lemma over there. Each positive root can be written as a sum of the simple root and the positive root, and the height of this positive root has to be one smaller than the height of the positive root here. And now the idea is that we can now describe the construction P1, so there's P2, there's P3, there's Pn, still not empty, gives Pn plus 1 is empty. But I'm only using the data of the Cartan matrix. So, SSP, I'm only using the Cartan matrix. Now, how can we do that? Well, first of all, we can take the formal, so we can give the elements of the index set of the Cartan matrix names. Right. Now let's call the set, and we shall set with S. So we have this matrix. And now we take for E, we take the formal direct sum. So it's really the vector space spanned by the basis consisting of the simple roots. Now, we know that these Cartan integers are, they are of the form 2 alpha beta alpha comma. And it's very good to realize that this is linear in terms of beta, because that means that we get the mu and alpha betas at every step, as long as we keep pairing positive roots with simple roots. So this is linear in beta. Now, so now what we are going to what we now know is that, for instance, what we could do is we could say, okay, really, because of this formula, the precise length, the precise normalization of the inner product doesn't matter. We could normalize it in such a way that a particular simple root is given length 1 by multiplying with the positive scale. But then we have seen that unless roots are perpendicular, in that case they have nothing to do with each other, as we will see. So we can divide the simple roots in groups that are as such that the spans are perpendicular. And for each of those components, the inner products can be normalized as we like. And so that means that basically we can normalize the length of the roots. If you think of the table that we started with. And so if you do that, then E becomes equised with an inner product. And in such a way that the shorter simple roots have like 1. And then the length of the other inner products are known. And the angles between the simple roots. So we now also have the notion of angle, and the angles can be read off from the table that we saw. Right? So that means that we now have this base E, and we have an inner product, and now we are going to fill in the roots. And the roots are going to be sums of simple roots. And that's, so we now have the set P1, S is P1, as a subset of E. And now what do we do to get P2? Well, we are going to look at beta plus alpha, where beta is an element of P1, and where alpha is an element of S. Of course, this is S, but later I want to see this as a pk, and this is pk plus 1. So maybe I should. So suppose that we have reached set pk. How are we going to determine set pk plus 1? Well, look at elements of this form. And now I have to decide whether this is a root or not. If it is a root, I add it to the positive roots. If it's not, I don't. And when is the positive root? Well, now I'm going to use my information about root levels. So I'm going to look at this. Actually, what I can do is I can look at beta plus alpha. Look at which roots, beta minus alpha, up to beta plus P alpha are still roots. This can be read off from the data that I have obtained already, because if I subtract simple roots from positive roots, I will get positive roots that have a lower height. So at each step I can decide this is a root that I have obtained already. This is a root in pk, this will be pk minus 1. If it is a root, until we arrive at a root in pk minus plus p, if it is a root. And here there will not be a root in. So here it stops. So we can speak about a p which depends on beta, and the construction we have done so far, and alpha. So let's call this a P alpha or beta. Now we know that for a root system, P alpha of beta plus Q alpha of beta is minus N alpha beta. Now this is known because beta has already been expressed as a sum of simple roots, and alpha beta is linear to beta, and therefore this can be determined from the Cartan matrix. But that means that Q is known. Q alpha beta is minus N alpha beta minus P alpha beta. So this is a known element of the natural numbers. Now, if it is at least 1, then we know that beta plus alpha has to be a root. So now, so the check is whether if this is 1, if this is at least 1, then it follows that beta plus alpha is a root, is a positive root of higher height. And if it is 0, then it follows that beta plus alpha is not. Does not belong to this. Now this process stops at some point. At some point we will not get any new root, and then we know that our positive system is complete. Now this in fact is a procedure which is completely independent So the way I've described it now is completely independent of information about the root system. The only information I need, this information, is the Cartan matrix, or the Dynkin matrix. So let's now look at the most complicated example, this one, more or less ended with last time, and let's construct the root system using this algorithm. Let's do it. And let's concentrate, and you should really do the other cases as well. Go over this reasoning, but let's do this in the most, let's do here in the most complicated situation possible. So, we have the case of the Cartan matrix 2, 2 minus b minus 1. This corresponds to the alpha, this to the beta. And so the Dynkin diagram looks like this. Okay, so we have, now we know that the root will be the angle between the roots should be. First of all, we know that the length of beta over the length of alpha is square root of 3. Alpha is a shorter root. We also know what the angle is. The angle of alpha and beta is 5, 5, and 6. Take from the table at the beginning of the at the beginning of today's lecture. So now, if we this determines really. Now, of course, we may normalize the inner product such that alpha equals 1. Okay, so we have a vector, and now, so let's draw this vector alpha. Of length 1. So we will know. Here we have beta somewhere, and now what we should do is we should take alpha here and then with factor 3 over 2. So this is where we should do. Okay, so we have beta, and we have our P1 consists of alpha and beta. Okay, now the question is, so P2. So what, the only possibility is take the sum of alpha and beta. This is an element of P2. Well, what should we do? Well, we should consider the root letter. Now, beta minus alpha is not going to be a root, because beta and alpha are simple. So, the root, so in this situation, the P alpha of beta is already 0. So we know that the Q alpha of beta is minus n alpha beta, which is, you can read it off from the Cartan matrix, is 3. And that means that beta plus alpha. Oh, this is of course not the right way to do this. This is. Let's forget about this. Yeah, it is about that. This is a hand, it's about this is beta plus alpha, and then we have so here beta plus 2 alpha, and then we know that the letter ends at Q, so beta plus 3 alpha. So that's this one plus that one. Now, of course, I mean, this element belongs to P2, this belongs to P3, and this belongs to P4. So I have already constructed elements of P2, P3, P4 along the way. But at first, we're really only interested in P2. Now, the only possible element of P2 is, I mean, alpha plus alpha cannot be a root. Right? We know that. Beta plus beta cannot be a root. So alpha plus beta is the only possibility. So P2 is beta plus alpha. Now, we know already that P3 contains beta plus 2 alpha from the ladder consideration. Now, of course, we could ask the question, does 2 beta plus alpha belong to P3? Is this, yeah, so really, I should really read this as beta plus alpha, root of P2 plus beta. Does this belong to P3? Well, what should I do? I should look at the letter, the beta letter, through beta plus alpha. So look at the beta letter through beta plus alpha. Well, beta plus alpha minus beta is a root. So this starts with alpha, and then alpha plus beta, and then, yeah, it ends with alpha plus q times beta. And we can calculate q, because we know what the starting point here is, corresponds to P0. So that means that Q will be equal to minus m beta alpha. Now this is m alpha beta, and this is m beta alpha. So minus minus 1 is 1. So that means that here we are at step 1 of the root letter. So if we add another copy of beta, then if we add beta one more time, I should say, we add the same copy of beta. If we add beta one more time, then this is not going to be a root. So answer is no. So we know that P3 consists of beta plus 2 alpha. And it is now just quite clear how we continue. So now we look at, so we have P3 now. And now we look at whether beta plus 2 alpha plus alpha is a root. Yeah, we have decided that already. But the other possibility is starting from this root, what happens if we add beta? Same reasoning. Then we're not going to get a root. But if we start with this root and we add beta, then we are going to get a root. Yes?
Can we determine Q then in this case?
We can determine Q. Would you like to do this?
Yes.
Let's do it. Okay.
In the previous case, B was 0 or minus 1.
In this case, yeah. Well, now I'm starting. I really view this now as, so the beta string through beta plus alpha is the beta string through alpha. And if I view it in this way, then the P corresponding to the beta string through alpha has to be 0. So note that I could have done this a bit differently. Let's do the calculation a bit differently. So what I could also have done is, we also first have determined the P, and then the P would be minus 1. So the P beta plus alpha would be minus 1. And now the Q beta plus alpha would be minus p beta, beta plus alpha, minus n beta, beta plus alpha. And now I'm going to use linearity in the second slot. So this will be minus p beta, beta plus alpha, minus n beta, beta, minus n beta alpha. And then this is now plus 1 minus 2 this right, I do this correctly.
Yes. Yes. It's not a plus 1 now.
Sorry.
You get not a plus 1 now, and then you do that.
This is exactly what I had before, right? Well, I had Q as 1, but of course, from this viewpoint, Q should be 1 lower. So we see that we do not need, and this is of course the step that I really described over there. Okay. Now, I think that you probably, I hope you now see how the calculation goes. We can go on, and at a certain point it stops. We do not get new roots, and then we have all our positive roots. And in fact, if you consider the beta string through this root, you will not get a root. And we can see it immediately, because then we would have 2 times beta plus 2 times alpha, which is 2 times a root, which cannot be. And so the only possibility is the sum of these two, which is 2 beta plus 3 alpha, which is also the sum of these two. And by doing this latter reasoning, one decides that this is a root. And then one sees that P6 is empty. So the process stops. Then of course one only has a positive system, but then by adding negatives of these roots, one gets the full root system. This is how it works. Now, on the way, last time and on the way, I already explained what the Dynkin diagrams are, and now I'm going to give a generalization. The possible connected Dynkin diagrams of root systems are those of type An with n at least 1, meaning that we have n vertices and they're all connected by a single edge. Now, Bn looks like this. At the end, we have a double arrow. We have a double edge, and the arrow is pointing towards the shorter root. Now, Bn only makes sense for n at least 2, because otherwise we would just have one dot, and then we would have the A1 situation. So in order to avoid double occurrences, we could say, well, let's do this. And we also have a series of Dynkin diagrams in the following form. We do the same thing, but we have the arrow pointing in the opposite direction. Now, of course, this case is only distinguishable from this case if n is at least 3. Right? Because then the single edge emerges from the longer group here and from the short group here. So that makes a difference. So in order to avoid double occurrences, we have to require this. And then finally, we also have Dn has the property that at the end there is a splitting like this. And here we have n minus 1, n minus 2. Now, of course, if we have this one, then we just have A3. So in order to have the new one, we start with 4. Now, these correspond, incidentally, to the classical Lie algebras, SU n plus 1, SO 2n plus 1, symplectic algebra at SO2n. These are called the classical series. And now the big surprise of the theory was that there are 5 additional Lie algebras. Simple can be for connected Dynkin diagrams, and they all correspond to simple Lie algebras, and they do not occur in a classical series. They are really surprises. And these are E6, E7, E8, F4, and G2. And let's draw them. So E6 looks like this, 5 like this, and I always to get E8, we want let's draw on this side. So this is by adding one more here to get E7, and then so this will correspond to E6, this to E7, and then one more corresponds to E8. And then we have F4, which looks like this. 4 indicates the rank of the root system, and we have G2, which looks like this. Now, what you see is that I'm speaking here about possible connected Dynkin diagrams. Now, what do I mean by that? Well, I mean, it's quite clear. Connected is quite clear, I think. Why am I speaking about connected Dynkin diagrams? Well, this notion corresponds to so-called irreducible root systems, which in turn corresponds to simple, compact Lie algebras. So these Dynkin diagrams classify the simple compact Lie algebras. Now we know that the semi-compact Lie algebras are all the sum, the direct sum of their simple ideals. Yeah. So this, and how do you get the corresponding Dynkin diagram? Well, basically by taking the disjoint union of the Dynkin diagrams of the connected components. So you get all Dynkin diagrams by taking this joint union of copies of from the list. And so if I give you a Dynkin diagram, you can precisely tell what are its connected components and what are the corresponding simple ideals. So you can read off the decomposition into simple ideals. Now, so for instance, and usually the notation is, suppose that you have a root system, R1 with E1, and E2 and R2. Then what we can do is we can take E1 plus E2, and then take really the union of this. And so this is how it works on the level of the roots. And if you have a Dynkin diagram here, Dynkin diagram there, and the Dynkin diagram of this root system is just the union of these Dynkin diagrams. And so on the level of real algebras, it's also take direct sums. Well, on the level of foreign, this is exactly what it is. So I didn't have time to give those final details here, but I think those are pretty obvious if you read the lecture notes. So I think this is a good point to stop.